Calculating probabilistic loss. 9. Go to cell I3 on Portfolio Data tab. On this cell, we calculate loss given default as the complement to a stochastic recovery rate. Recovery rate will be modeled with a truncated exponential function. Cell I3 should now contain the following formula. Equals 1 minus risk expon, open parenthesis, beta, comma, risk truncate, open parenthesis, 0, 1, close to parenthesis. The subclass risk truncate within the expon distribution function limits the minimum and maximum allowed values for random numbers to be generated by it. Hence, it will not generate negative numbers or numbers above 100%. To calculate loss given default, we subtract 1 minus the simulated recovery rate. Cell param C33 has been previously named beta in Excel. Notice the probabilities of default, PDS, have already been given in this exercise according to the following table in params. Depending on type code for each loan, the probabilities of becoming default for each type of credit have already been provided. For example, the probability of default for a loan on score level 4 for a consumer loan is 4.23% in 1 year. 10. On cell J3, insert the following formula. Equals VLOOKUP, open parenthesis, E3, comma, PDS, comma, C3 plus 1, comma, 0, close parenthesis. It calculates the respective probability of default for any particular loan depending on its score interval and the type code, whether it belongs to a mortgage, vehicle, or consumer type. The PDS range has already been defined as the lookup range for this function to work properly. 11. On cell K3, the following formula calculates expected loss multiplying PD times LGD times EAD. Its formula is equals H3 times, open parenthesis, 1 minus beta, close parenthesis, times J3. Notice that since this is the deterministic or expected loss calculation, we're using the same average level of LGD for each loan. In other words, beta. 12. On cell L3, we formulate a binary representation of default. Any particular loan either defaults 1 or not defaults 0 based on a certain PD. Therefore, we can build the following formula to stochastically generate zeros and ones based on a Bernoulli or binary at-risk function within the formula equals risk Bernoulli, open parenthesis, J3, close parenthesis. 13. By clicking on at-risk's define distribution button, you can see the binary representation of this discrete distribution function. In this case, for example, on close to 99% of the time, a 0, no default, will be generated, and on close to 1% of the time, a 1, default, will be simulated. 14. Cell M3 picks up the eventual loss by formulating as follows. Equals H3 times I3 times L3. Notice that on this formula, instead of using PD on cell J3, we use the L3, which now only contains either a 0 or a 1. This is essentially the difference between the expected loss approach and the probabilistic approach on the calculation of losses. 15. Copy the range I3, M3 all the way down for the remaining of the range of loans. With the random/static standard F9 recalc button or the dice icon on, press F9 several times to recalculate these columns and observe its effect on various iterated scenarios. 16. On cell K1, sum the total expected losses by writing the following formula. Equals sum K3 through K502, close parenthesis. 17. Copy cell K1 to L1 and M1 to calculate, respectively, the total number of loans that turn to default and the total simulated losses. 18. Both cells L1 and M1 should be declared output variables on at-risk. Place your cursor on L1 and click the Add Output button, naming the output variable as defaults. 19. Place your cursor on M1 and click the Add Output button, naming the output variable as loss. 20. Now it is time to simulate. Place your cursor on cell M1 and turn on Start a simulation with 5,000 iterations.